Okay, so the next homework problem is 1.10 in the Incropura book, Fundamentals of Heat and Mass Transfer. It's the version from 2007. But anyway, so we have a 5 millimeter. I'll let you go ahead and read this problem. But we basically got a pot here with a round circular bottom. This is not a very good drawing, but you get the idea of what's going on. Round circular bottom. And then we've got heat going into it, just like this, going up through it like that, from a burner top. This is a terrible drawing, but like I said, you guys will get the idea. We're actually going to just do the first half of it here, made from either aluminum or copper, as you can see up here. We're just going to do the aluminum version, because the copper is exactly the same, and it doesn't really matter. Copper will be a better conductor at the end of it all, but nobody cares. Okay, so the water, we know that the T in here, we're just going to say T dot is equal to 100 degrees C. This is Q. And heat is transferred from the stove at a rate of 600 watts. This is actually equal to Q, because heat is transferred to the pot. So heat transfer, the rate of heat transfer is 600 watts, or 600 joules per second, however you want to do that. But you know that this is Q. So what is the temperature of the surface in contact with the stove of each of the two materials, so of the one material? So we're going to go ahead and look at this T right here. This T is equal to question, and we're going to say this one is T stove, and this one's actually going to be T water. Oops, sorry. Let me get rid of that T dot. T water at this point. Okay. We also know that the diameter of the pan is 200 millimeters. And we know that it has a thickness of 5 millimeters. Okay, so going ahead and putting this into our heat transfer equation, stuff out of there. We know that our heat transfer equation is Q is equal to K times the area that you're moving through, T1 minus T2, so the highest temperature minus the lowest temperature, all over the thickness of the material. This is the area you're transferring through the thermal conductivity. We're going to rearrange this because we're looking for TS. And we know that TS is actually going to be higher because the heat is traveling this way, so the water is absorbing it. So this is actually going to equal Q, or Ka times TS minus TW all over L. And then rearranging this, we have TS is equal to TW plus Q L over K A. We know we can get this, we can get this, we have that, we have that, and we have this. And for aluminum, well, yeah, we have K. For aluminum, K is equal to 240 watts per meter Kelvin. This can actually be looked up in the back of the book, in the appendices of the heat transfer book, if it's not given to you in a problem. So so that's it, basically. We have this equation. We know that the area is equal to pi d squared all over 4, which is going to give us 0.0314 meters squared if you plug in that diameter. Alrighty, and convert it to meters, of course, so 0.2 meters. And then, so T1 is going to equal 110 degrees C plus 600 watts, which is Q, times 0.005 meters, which is the thickness, or L, all over 240 watts per meter Kelvin, times the area that we're moving through, so 0.0314 meters squared. And again, if you haven't seen this before, we've got a degree C and a degree Kelvin here. Temperatures in C and temperatures in Kelvin, when they're being added or subtracted, can basically remain the same because the differences of those two respective unit systems are identical. So, I mean, 10 degrees difference in Celsius is the same as 10 degrees difference in Kelvin. So you can basically ignore that, and you know it'll all cancel down to Celsius if you want to. If you want to, you can go ahead and convert this, just make sure there's no confusion anywhere. But if you do all this math and just simplify it down, and ignore units, the number you'll get out is equal to 110.40 degrees C. So this is the temperature that the stove has to be at in order to heat the water to 100 degrees C. So it's a pretty good rate of heat transfer there. And if you happen to do the copper here, I'll just give you the answer for that one. For the copper, T1 is equal to 110.24 degrees C. So a little bit less than the aluminum, which you can expect because copper is actually a better conductor than aluminum. But that's how you do it. You just go ahead and take the standard heat rate equation and you rearrange it to get T1 and you solve it. So, bing, bang, boom.